All right, how's everybody doing today? Sorry I couldn't be there to teach you guys in person, but sometimes that's just the way it be. So today we're going to be talking about the kinematic equations, and these are essentially how we can mathematically model motion. So we've talked about motion graphs, we've talked about collecting data on position and time and graphing that, and we're actually going to use those graphs then to come up with some equations that we can use to generally describe motion for any objects that have a velocity, have an acceleration. And we can track their position, track their velocity, and all those things through time. So that's what we're going to get at today. Definitely follow along with this in your notes. You'll want to have these equations in your notebook. We'll be using them for the homework today, and we'll be using them throughout the rest of the quarter. We'll start off with the joke of the day. Why shouldn't you write with a broken pencil? Well, because it's pointless. Get it? Get it? It'd be totally pointless because it's broken. Anyways, moving on. So here we go. A little recap of what we did the other day. We did this fan cart video analysis. We had the video with the fan cart and we tracked its position using this little yellow tape through time. And because we knew how many seconds a frame was, each frame represented, which was 1/30th, and we knew how many pixels 1 meter was, it could calculate its exact position relative to the origin, which we set as right here. We could track its position through time. All right, and then we graphed that in this position time graph, which we applied a quadratic fit to, and then this program also creates for us, calculating from this position time graph, it calculates the velocity at any given time and plots that as a velocity versus time graph. Right. And then it gives us these equations. If we do a quadratic fit for this curve, right, this nice curved parabola. If we ever have a parabola, we want to do a quadratic fit for that. And if we've got a nice straight line like the velocity time graph, we do a linear fit. And we notice both of these graphs seem to indicate to us that this fan cart was speeding up in the positive direction, which is to the right. And there are a few conclusion questions I had you guys consider. And I want to talk about those right now because a few people were a little bit off on these. And so I want to set the record straight. The first one, and this is a big one, is what is the acceleration of the fan cart? Well, a lot of you guys saw this little a here on the quadratic equation that I gave you and thought, or assumed rather, that that is the acceleration. That is not the acceleration of the fan cart. As we remember, acceleration is the rate of change in velocity, right? And the velocity graph shows us that the velocity is increasing over time. And what is the rate at which the velocity is increasing over time? Well, we find that by finding the slope, right? So the way that we've learned before is you can take 2 points on our line of best fit. And so I see kind of this point right here and this point right here are pretty close to being on that line. And so we can use those to find the rise and the run and calculate the slope. So here this point is 1.5 seconds by 0.15 meters per second. And this one is 4 seconds by 0.3 meters per second. So we can calculate our rise over our run. And our rise in this case happens to be, it goes up by a positive 1.5 to 0.35, sorry. So that is up by 0.2. So this is 0.2. Sorry, let me do that with the pen. This is 0.2 meters per second. And our run happens to be, let's see, 0.5. So that's 2.5 seconds. 2.5 seconds. So our slope, our rise over our run, is 0.2 meters per second over 2.5 seconds. And if we plug that into our calculator, we end up with about 0.08 meters per second, right? So that ends up being our acceleration. Now you'll also see that's pretty darn close to this number that we get down here, the m. And if you remember anything from math class, you see this equation for a straight line, the m represents the slope of that line. So that makes sense. This is the acceleration. So we want to plug in for what is the acceleration of the fan cart. It happens to be 0.08 meters per second. So that's the acceleration. Now you'll notice this little a down here that is related to the acceleration. You may happen to notice that that is half of the acceleration. right? And we'll talk about that a little bit more later. But remember, the acceleration, the best way to find the acceleration is it's the slope of the velocity time graph. It's the rate of change in velocity over time. Net force, this one's pretty straightforward. You just got to remember that we don't use grams for mass. We want to convert that to kilograms. So that is 0.4 kilograms. So we have net force is mass times acceleration. That's Newton's second law. So that means our net force is our mass, 0.4 kilograms, times the acceleration, which was 0.08 meters per second. And that gives us a net force of 0.032 newtons, right? So is that a very big net force? It's not super big, but keep in mind that it's a relatively low friction track, right? So the amount of friction on this track is really low, and so that allows the fan cart to accelerate, albeit slowly. You'll notice that the net force from that fan is not really making it accelerate that quickly, so it's a relatively small net force. How does the fan blade generate a net force? Quick little reminder on Newton's third law. Right, that fan blade pushes back on those air molecules, and those air molecules push forward on the fan blade with an equal and opposite force. So that's how it can actually generate that force to push it forward. If this track continued, what would you predict the velocity of the cart to be after 11 seconds? And these two I want to take a pause on, right? So we're looking for the velocity and the position after 11 seconds. And the best way to do that, really, is to take a look at our graphs here, and if you were to extend these graphs to where we could get 11 seconds on the x-axis, you want to make a prediction as to where the position and the velocity would be. So I do want to show you guys how to do that. I have our video analysis up here. And what you can do is I have my velocity graph up first, we'll do that first. If I apply my linear fit, and then I can go to these graph options and I can change my scale. So I want my x-axis, which is time, to go up to 11 seconds. And I'll change my x-axis range to, so I can see that there. And so I see that after 11 seconds, if I follow this over, it's at right about 0.9 meters per second, right? So I would plug into here, I would say it would be about 0.9 meters per second is what I'd predict, right? Just based off of looking at my graph and my line of best fit. And then similarly with the position, if I change this up and do my position graph and apply my quadratic fit to there, that nice fit, and then I can change the axes of this too to go up to 11 seconds. We say I need quite a bit more, so let's go to 5. I don't need a little bit more, so let's go up to 6. And if I close this out now, and I follow this along here, I see it's right around like maybe 5.2 would be the position down the track after those 11 seconds. So I can plug that in here. I would say it would be about 5.2 meters per, not meters per second, 5.2 meters would be its position on the track after that point in time. Right, so those are my predictions just based off of looking at those graphs. Now, one great thing is by using these graphs and using these calculations and the data I collected to find the acceleration of the cart and knowing its initial velocity and its starting position, what I can do is I can actually take these lines of best fit, they can be represented by equations, which are given here, right? These equations can then actually be written out to describe the position of the cart at any given time and the velocity of the cart at any given time. And we're going to dive into how you do that, but essentially really what it boils down to is seeing what each one of these little variables represent in these equations that they provide us. Right, so that's the next step here, and that will allow us to make more accurate predictions even than just looking at a graph like that. So let's start with this first one is that we'll do is the velocity time graph. And I'm going to try and find, using this, I want to find the equation that represents what is going to be the velocity at any given time. Because that's what this graph is showing. It's showing the velocity over time. I get this nice linear fit, and it gives me this equation, y equals mx plus b. Okay. y equals mx plus b. And this is the general equation for a straight line, right? For a linear fit, for a straight line is this equation. And you may know that the m, we already talked about this, the m represents the slope. You may be familiar with the b representing the y-intercept. But what do these y and the x represent? Well, those just represent whatever variable is on my y-axis and whatever variable is on my x-axis, right? So on my y-axis, my variable here, right, this is actually its velocity. There we go. That is its velocity. So the velocity is my variable. It's on the y-axis. And that velocity then is equal to my slope, which we already talked about. That slope is the acceleration. Okay, so the slope is the acceleration. And the x, as we mentioned, is the whatever is the variable on the x-axis, which happens to be time in this case. So the x is time. And then our b is the y-intercept. And the y-intercept represents, in this case, it's when the time is 0. When our x variable is 0, when the time is 0, what is the y variable? What is the velocity, right? Well, when the time is 0, the velocity, in this case, happens to be about 0.03, right? But this is the what we call the velocity initial, right? Which is the initial velocity, or the starting velocity. Right, so this is VI. That's the initial velocity right there. And so we'd say plus the initial velocity or the starting velocity. So this is our first kinematic equation. The velocity at any point in time is equal to the acceleration times the amount of time that has passed plus whatever the initial velocity was. I'll kind of label those in here. So this is our velocity at any point in time, our velocity at any point in time, measured in meters per second, is equal to our acceleration, and that's in meters per second, times the amount of time that has passed, so seconds, plus whatever the starting velocity was. And that's, of course, in meters per second. Okay, so that is our first kinematic equation, is this bad boy right here. And so for the fan cart, for example, what we'd write out for is we'd say the velocity at any given time is equal to its acceleration, which is 0.08 meters per second, times whatever amount of time that we want to input, plus the starting velocity, which we said was 0.03 meters per second, according to our model, right? And so using this equation then, right, now if I were to say, hey, any amount of time, at this point in time, what would you predict the velocity to be? Well, we could do that. So if I wanted to know, hey, what would the velocity be after 11 seconds? Well, I'd plug in 0.08, multiply by the time, which is 11, and add the initial velocity, which is 0.03, and that says that the velocity after 11 seconds should be around 0.91 meters per second. And we can see how that compares with what we got here, and it's pretty darn close, right? Pretty darn close. And so this is how we can actually then create a model, an equation that we can use to make predictions. And this can be these equations can be very useful if, for example, we don't have the graph, if we didn't collect the data ourselves, but rather we're told an acceleration, or we calculate an acceleration using net force, right? Or let's say that I want to solve for the amount of time it'll take something to get somewhere, and I know its velocity, I know its acceleration, and I know its initial velocity. So if I want to calculate the amount of time it'll take it to get to a certain velocity, I can do that, right? So this equation then we can apply. If there's any one of these that we don't know, we can, and we know the others, we can use those to solve for the unknown. Okay, so this is kinematic equation number 1. Kinematic equation number 2 deals with our position time graph. Okay, so our position time graph is dealing with the position, in this case the position on the x-axis, through time. And we saw it was a parabola, so we applied a quadratic fit. And the general equation for a parabola is the quadratic equation, which is y equals ax squared plus bx plus c. So we'll put that in there. Right, y equals ax squared plus bx plus c. Now these a, b's, and c's, these are just placeholders. They're just constants, right, that determine the shape of the parabola, right? The a essentially represents how steep the parabola is, right? If it's going to be super steep, right, it's going to have a big A. If it's going to be a little shallower, it's going to have a low A, right? And then the B represents the initial steepness of the parabola. So see how this one starts kind of flattish, right, and then gets steeper, right? If it's got a higher B, it's going to start a little steeper and then keep getting steeper from there, right? So a high B might look like that, whereas a low B might look like that, or a negative B might actually look like this, right? It might actually go down and then up. Okay, so A determines the steepness, B determines the initial kind of slope, and then C actually determines where it is. So if it has a C of 0.4, it's going to be starting up here. Right? It's going to be crossing the x-axis or the y-axis there. So that's the general form of an equation for a parabola. And so these numbers each kind of represent something. Now I already talked a little bit about what this A represents. And I said that we said 0.04, and we noticed that that is actually half of the acceleration. And that's a big deal, so we note that. So this A that it gives us here, when we apply this quadratic fit, that actually represents 1/2 the acceleration, right? Our y value, once again, is whatever is in the x-axis, right? So in this case, our y value happens to be, and this is kind of confusing, so I apologize for that, the symbol we use is x, right? And that represents the position in the x dimension, right? So this is the position. In this case, it's in the x dimension. And that is, of course, measured in meters. Okay, and then we mentioned that this A then actually represents, right, half of the acceleration. So this A represents 1/2 the acceleration. And this 1/2 is just like a general 1/2. Right? So this represents kind of this whole part is what the A is. Our x variable here in the x-axis is time, just like the last one. So this then, we go down, and that is t squared, right? So time is squared, plus bx plus c. So what does the b represent here then, right? What does this b represent? And that b ends up representing, right, if we remember, that happened to be our y-intercept, right, our initial velocity. So this b actually represents, this is the vi, or the initial velocity. V is the starting velocity. So we'll put that down there. This is our initial velocity. And then our x, once again, is the time. And the c in this case, you'll notice, happens to be pretty darn close to 0. And 0 happened to be our starting position. Right, so this is our starting position. right? And so that is what we call xi, or our starting position. And c is going to represent the starting position. Right. So when we string it all together, this is our second kinematic equation, right? The position at any point in time, right, is equal to half the acceleration times the time squared plus the initial velocity times the time plus the starting position, right? So this one is a little bit more complicated. I'll go ahead and fill these in here. Right, this A, as we mentioned, represents acceleration. That is in meters per second, or meters per second squared, right? The VI, that is, once again, that is our initial velocity. It's in meters per second. And that's just, once again, the velocity that it's starting with, the velocity at time 0. And the xi, right, this is the initial position. Right, in meters, or the position at time 0. So at time 0, whatever we choose to be time 0, right, what was its starting position? VI is whatever time 0 was, what was its starting velocity? And then, of course, t represents time, and that's measured in seconds. Right? So there we go. So that's what this all means. Now, this equation is a little bit bigger, a little bit more intimidating, right? But we can still use it just like any equation, where if we have certain variables that we know and certain variables that we don't know, we can solve for unknowns and we can make predictions, right? So similar with our fan cart, if I wanted to make a prediction, oh, still on red. So similar with our fan cart, if I wanted to make a prediction about its position at a certain point in time, given its acceleration, given its initial velocity, given its starting position, I could write an equation to describe that, and that would be its position at any point in time. Any point in time is going to be equal to 1/2 its acceleration, which was 0.08 meters per second, right? Now you'll notice 1/2 of 0.08 is that 0.04, right? Times the time squared plus its initial velocity, which is 0.03 meters per second, right? And then multiply that by the time as well, plus the initial position, which we're gonna round that. That's pretty darn close to 0, so we're just gonna say that's 0 meters, right? And that's the equation that I could use. So if I wanted to know its position after 11 seconds, I could plug in 11 for the time and calculate that out. So if I take 11 squared and multiply that by 0.04, I get 4.84, and add that to 0.03 times 11, which would be 0.33. I end up with 5.17 meters. And we can see that is, once again, really close to what we just got looking at our graph, right? So these equations then, these two kinematic equations are useful because we don't necessarily need the graph, right? We can actually use these if I just know the acceleration, I know its initial velocity, I know its starting position. You tell me a time, I can calculate its final position, or its position at that point in time. If you tell me, if you want to know when an object is going to be at a certain position, right, given its acceleration, its initial velocity, and starting position, we can solve for that too. So these are very powerful. We're going to be using these throughout the rest of the quarter. We'll be using them on the practice problems, which are your homework for today. So we'll get very comfortable with them. One thing of note with this equation is if the acceleration is 0, right? In other words, it's not accelerating, its velocity is not changing, right? Then if this is 0, this whole part of the equation becomes 0. Instead, we're just left with the position is equal to the velocity times the amount of time that's passed plus the initial position, right? And so that's one that where if it's not accelerating, it becomes a lot easier, a lot simpler of an equation. And so, but this is the full equation that is more useful if we do have accelerations. Okay, so those are your two kinematic equations. We'll be practicing them in the homework. Definitely make sure that you guys have those in your notes and feel comfortable with them. And I look forward to seeing you guys tomorrow.